All right, so this is a big section, partly because what it involves is a lot of the prerequisite material that you may or may not really remember very well. In particular, we're going to be talking about things like factoring and completing the square. And I'm just going to build all of those skills into what we're going to be talking about in section 3.2. So when we talk about quadratics, which I claim we've actually already done, what we're talking about are second degree polynomials. Okay, so the one we're most familiar with is y equals x squared. Okay, so when I say we've already talked about these, this is the one in particular I'm looking at. So recall that we have this as our graph. Okay, what I want to mention is as follows. We call the shape of this graph, it's called a parabola. And we can talk about the domain and range of these functions. The first thing I want to mention is that the domain is all reals. Okay, we have no limitations as to what we can plug in for x here. We don't have to worry about taking square roots of negative numbers. We don't have to worry about dividing by 0. Now, in terms of the range, well, that depends upon the function. Okay, because these things can be shifted and moved all over the place. For example, the range here would be from 0 up through infinity. Okay, but these graphs can also be down here or way the heck up here. Okay, in general, when we talk about the equation of a quadratic, we say it's of the form ax squared plus bx plus c. A, b, and c are real numbers. And the only rule is a can't be 0. Simply because if a was 0, that would nix this first term. And then notice we're left with a linear function, right? Because my highest power is 1. So some things that are notable about these graphs is we talk about what's called our vertex, okay? In this case, this is our vertex, here's our vertex here, and here's our vertex there, okay? Notice that's the point where our function changes from either decreasing to increasing or increasing to decreasing. So for our general quadratic, our vertex is at the ordered pair 0, 0. Okay. And the important thing to mention is that the vertical line passing through the vertex is called the axis of symmetry. Okay, so in this case, my axis of symmetry would be x equals 0. Recall the equation of any vertical line is x equals whatever the x value is. Okay, now, what's cool about this is we call this the axis of symmetry precisely because if we were somehow able to fold our graph through our vertex along this axis of symmetry, one side of our graph is a mirror image of the other side. Okay, so in general, when we have a quadratic, ax squared plus bx plus c, okay, what we know is that the graph opens up. In other words, if here's our vertex, it opens up. If our leading coefficient is positive, and it opens down. In other words, if here's our vertex, it opens down if our leading coefficient is negative. Another thing to point out is if our quadratic is written in this form, the vertical intercept is simply the value of c, precisely because we find our vertical intercept by setting x equal to 0. If we do that, that will get rid of these two terms, and we're simply left with c. Okay, notice this translates back to what we talked about in section 3.1. Now, when we talk about quadratics, there's three basic forms, and they all have their advantages and disadvantages, and you can move from one form to another, okay? The general form, which we have written above, looks like this, okay? It's when it's just simply written out in descending order of our exponents. The nice thing about the general form is it's really, really simple to read off what your vertical intercept is. I think that's the biggest advantage of this form, okay? Again, because once you plug in x equals 0, that just nixes any term with an x in it, okay? Another form that we're going to encounter, which is really useful, is what we call our factored form. And our factored form means essentially that we factored it. Okay, not every quadratic can be factored, but when we can factor it, the beautiful thing about the factored form is you can read off your horizontal intercepts or your zeros. Okay, so again, with the general form, the plus is you can read off your vertical intercept is just at C. The positive here is you can read off your horizontal intercepts or your zeros. Okay, recall the reason why is to find our horizontal intercepts. We set this equal to 0. Well, I claim that's going to tell me that P and Q are my zeros. Okay, again, why? If I set this equal to 0, well, the A is just a constant. It's not going to have any effect. And what makes x minus P equal to 0 is if x is equal to P. And what makes x minus Q equal to 0 is if x is equal to Q. A third form that we can have is what we call our vertex form. And that's when we're able to get our quadratic written like this. And the positive thing here is you can read off your vertex. In this form, I claim that my vertex is HK. Notice my H has the opposite sign here, and my K has the same sign. And knowing your vertex is very helpful because you know that one side is a mirror image of the other side. Okay, now expounding upon this, for general quadratics, and this is particularly interesting when we start talking about word problems, the vertex is either the high point if the graph goes down, and is the low point if your graph opens up. Okay, let me show you. If our parabola opens down, here's our vertex. It's the high point. Okay, this is my vertex, HK. I know that my leading coefficient is negative because this opens down. And notice that the range of this graph, our domain doesn't change, it's still all reals, but the range is all values of y less than or equal to k. Similarly, if our graph opens up, my vertex is my low point. We know since our graph opens up that our leading coefficient is positive. And here for our range, our y values are greater than or equal to k. All right. Now, I want to talk about each of these forms, and we're going to play around with each of these forms and how to get from one to the other. Okay. Now, what I want to say is if you're given this general form, again, I mentioned that the positive thing is that you can just read off what your vertical asymptote is. One way to find the vertex when it's in this form is as follows. Your x value for your vertex, notice A, B, C, these are just numbers, is x equals negative b over 2a. Okay? Now, how do you find your corresponding y value for your vertex? What you then do is you then plug in that value of x into the function to get the corresponding y or function value. Now we're going to learn another way of doing this, but this is a shortcut method that I would just not be a good teacher if I didn't tell you this. Okay. So, for example, if I have this quadratic, okay, one of the things that you're going to need to do when you're given a quadratic is always identify what your A, B, and C are. In this case, my A is 1, my B is 4, and my C is negative 2. Okay, these are just the numbers that we have here. If we wanted to find our vertex and axis of symmetry, well, using this above, I would say, well, the x value for my vertex is negative b. If b is 4, then negative b is negative 4 over 2 times a. Well, this gives me negative 4 over 2, which is negative 2. That's the x value for my vertex. Now, in order to find my corresponding y value or function value, what I'm going to do is compute f of negative 2. We know how to do that. It means everywhere where we see an x in our function f, we're going to plug in negative 2. By doing that, we're going to get 4 minus 8 minus 2, which is negative 6. So my vertex here is negative 2, negative 6. And my axis of symmetry, recall, is just the vertical line passing through that point. In other words, x equals negative 2. Now, we already can even know what this function looks like. Okay, first off, I know that negative 2 negative 6 is my vertex. I know this opens up because my A value is positive. And one other point, again, that's very easy to find when you have it written in this form is your vertical intercept. I can certainly compute f of 0. I just get negative 2. So notice that since this is symmetric for my vertex, if I go 2 to the right, I'm up at negative 2. which tells me that if I go 2 to the left, I'm also at -2. And there's my graph. Not quite so pointed, but there we go. All right. Well, what if I have this example that we want to find our vertex and axis of symmetry? Okay. Well, you might say, wait a minute, there's no x term. Well, sure there is. We can certainly rewrite that in this form. Notice here my A is 2, my B is 0, and my C is -5. So in this case, my vertex is -B over 2 times A, which is 0. Okay. And I can then find my corresponding function value. If I plug 0 into my function, I'll get -5 out. So here my vertex is 0, -5, and my axis of symmetry is x equals 0. I can essentially say if this is -5, this is about what my graph looks like. Again, it opens up precisely because my leading coefficient is positive. All right. Now, we can play around with this, not that you're going to be given that many exercises, but this is a really, really good way to just play around with problem solving and that sort of thing. What if we want to do this? Find the values of B and C so that f of x equals -8x squared plus bx plus c has a vertex at 2, -7. Okay, notice we have the value of A. We know that A is -8. What we want to find is what are my values of B and C. Okay, well, what we do know is that the x value for our vertex in this case is 2. And that, by definition, is -B over 2A. So I don't know B, but I sure know that A is -8. So what I have here is 2 is -B over -16. Well, negative divided by a negative cancels out. And we can certainly solve this for B. How do we undo division? Multiplication. So I'm going to get B to be 32. So thus far, we have -8x squared plus 32x plus c. All right, one more piece of information. We are also given our function value at 2. We know when we plug 2 in, -7 comes out. Well, what is f of 2? We have -8 times 2 squared plus 32 times 2 plus c. And we know that's got to be equal to -7. All right, well, 2 squared is 4 times -8 is -32 plus 64 plus c. So we have 32 plus c is -7. And we can solve for c by subtracting 32 to get c to be -39. So our function is -8x squared plus 32x minus 39. All right. Now, there is another way to find the vertex if the function is in general or standard form. So if we have our function in this form, which we call general or standard form, there is a way to write this in what we call vertex form. In other words, starting out in this form and changing it to that form. It's by a method called completing the square. Okay. Now, there's an advantage to being in vertex form. It's kind of a pain to get it into vertex form, but the advantage of being in vertex form is we can jump back to chapter 1 and we can use transformations to graph it. Okay. What do I mean? Well, let me just take something. Here's a quadratic in vertex form. Okay. I claim that what we've done is we've taken our general quadratic, y equals x squared. When you subtract 2 within, we go right 2 and then up 3. Well, if I take this and go right 2 and up 1, 2, 3, there is my parabola. And notice our vertex is 2, 3. Okay. Another example is, what if I have y equals -3, x plus 4 quantity squared minus 5. Now, as I mentioned before, you can read off your vertex. Remember, it's the opposite sign here, same sign here. Okay. But notice we can take our general quadratic y equals x squared. I'm adding 4 within my function, so that says we go left 4. This one here says, notice that we're going to reflect it. We have a negative in front. And we're going to go down 5. So if I take my general quadratic like this and I go left 4, and down 5, I know that this is going to open down because my leading coefficient is negative. There we go. So the question we can ask is, all right, how do you put a quadratic in vertex form? So what I'm going to do is write out those steps. So to put a quadratic function in vertex form by completing the square, here are the steps we're going to follow. Okay. All right. So the steps we will follow are, first, if the leading coefficient, in other words, the number in front of the squared term, is not 1, what you need to do is you need to factor it out of the first 2 terms. And the first 2 terms only, because we need to have a 1x squared. The second thing we're going to then do, and this is going to seem funky, but as always, you know I go through a ton of examples, is you're going to take half the middle term. And when you do that, you're going to write that number to the side. Then you're going to square it. And then what I'm going to say is add it in the parentheses, and you'll see what I mean momentarily, and then balance at the end. And our third step that we have is you're going to want to write the stuff in parentheses as some quantity squared. And the number that you use is what we wrote to the side in step 2. So use the number from step 2 that you wrote to the side. Okay, I totally get that this just seems like abstract nonsense. Bear with me. Let's go through several examples. Okay. So let's take our first example. What if I have x squared minus 2x minus 3? And what we want to do is we want to write this in vertex form. Okay. Well, step 1 says if the leading coefficient is not 1, you need to factor it out of the first 2 terms. I claim step 1 is a non-issue. Okay. So what I'm going to do from here is just kind of put parentheses around my first 2 terms. Okay. Now what we do is we go to the middle term and we take half of the middle term. Well, 1/2 of -2, remember of in math is times, is -1. Okay, this is the number that we write to the side. Take half the middle term, write that number to the side. My next step then is to square it. Well, when you square it, -1 squared is 1. Okay. And now what we're going to do is add it in parentheses and then balance it at the end. In other words, I squared it, I got 1. I'm going to add it in parentheses, but you can't just add something to a function without balancing it at the end, right? Because if I just add 1, then what I have here is x squared minus 2x minus 2, not my original function, okay? So life is about balance. If I add 1 in here, I got to subtract it out here. All right, my last step is to write this in parentheses as some quantity squared. Okay, well, what number goes here? Remember, I told you to, once we took half of the middle term, write that number to the side, -1. And -3 minus 1 is -4. Okay, so we have now written it in vertex form. I claim my vertex is +1, -4. And you can also use that shortcut -b over 2a to verify that you're going to get the same thing. Okay, let's take another example. What if I have y equals 2x squared minus 12x plus 11? Notice in this example, we do have a term to factor out. Remember, we want a 1 in front of our x squared, but you only factor it out of the first two terms. So I'm going to write that as 2. Well, if I factor out a 2 for my first term, I'm left with an x squared. If I take this term and divide it by 2, I'm left with minus 6x. And then I have plus 11. You can distribute here, and you will see that you get exactly what we started with. We're not changing the value of the function. We're just rewriting it in a different form. All right. Step 2, take half the middle term. Okay, notice this is literally in the middle. Okay, if I take half of -6, I get -3. If I square -3, I get 9. Okay, now what my next step says is add that number in my parentheses, but balance it out at the end. Notice I still have this plus 11, but I'm not going to just subtract 9 here, because notice this is in my parentheses, and if I distributed my 2, I've actually added on an 18. So in order to keep my equation the same and keep balance, since 2 times 9 is adding on 18, I need to subtract off 18 at the end. All right, I want to write this as some quantity squared. First off, 11 minus 18 is -7. What number goes here? Recall the number that goes here is what we got when we took half of the middle term. So here, our vertex is 3, -7. Remember, opposite sign, same sign. Okay. Now, one other background piece that we need to do here is as follows. To find our horizontal or x-intercepts, ideally, if they exist, I should say, we're in this form and we can find them. Recall the way you find your horizontal intercepts is you set this equal to 0. Well, this won't make it 0. You can set this first term equal to 0 to get p. You can set the second term equal to 0 to get q. Okay? Now, when we're dealing with quadratics, we actually have a few different situations that we can be in. Okay, it can be way up here or way down here, for example. Notice here, we have no horizontal intercepts. Okay, this is never going to touch or cross my x-axis. We could be right here where our vertex lives on our x-axis. And in this case, notice we have exactly one horizontal intercept. One place it touches or crosses our x-axis. And finally, we could be in a situation like this or like this. And notice in either one of these situations, we have two horizontal intercepts. Remember something that we saw before is that a polynomial of degree 2 can have 0, 1, or 2 x-intercepts. And here we have pictures of all three possibilities. Now, when you're in this form, you're psyched, right? Because to find it, you set f of x equal to 0 and you solve. For example, What if I have this? If I want to take this and find my intercepts, what I'll do is I'll set it equal to 0. Well, the 3 is not going to make anything happen here to get this to be 0. Okay, we're going to use our 0 property, and we're going to say either our first term is 0 or our second term is 0. And we can solve each of these for x. So we have 2x intercepts here, 4 and -1. Okay, this is a sweet situation. This is an example where we have 2 intercepts. Let's take this example. What if this is the way I'm writing my quadratic? Okay, we could multiply this out. I urge you to FOIL it. You're going to get x squared minus 10x plus 25. But if all we want to do is find our horizontal intercepts, what we do is we take this and set it equal to 0. Well, you could say, well, what does it mean to have this squared? It means you're taking it and multiplying it by itself. You got the product of two things equal to 0. Either the first one is 0 or the second one is 0. Redundant statement. Notice here, we just get 1 intercept. And then we could be in another situation where there are no intercepts. Okay? But in general, there are 3 methods to find our zeros or our horizontal intercepts. When it works, this is the cutest. That's factoring. Okay, but this does not always work. The next 2 do always work, but one is a lot more fluid to use than the other. You can do completing the square, or you can use the quadratic formula. Okay, so we started out this section, and what we've done so far is we've found the shortcut way to find the vertex, and then we've taken a quadratic in general form and learned how to write it in vertex form. Now what we're honing in on is how do we find our zeros? Okay, again, this is the cutest if it's factorable. These 2 methods always work. I have a very strong bias toward using my quadratic formula. Okay, but what I'm going to do right now is I am going to do a little more background work on factoring, in case you're not remembering these ideas. Okay, once I do this background work of factoring, then what we're going to do is pull all of these ideas together and complete this section. Okay, so here is a tutorial on factoring. Whenever you're asked to factor something, the first thing you want to do is pull out any common factors. Okay, we've done this, but let's practice. Suppose I have this. Okay, these are 2 terms. What do they have in common? Well, numerically, they have a 3 in common. And in terms of variables, they both have an x. If I pull out or divide each of these terms by 3x, well, my 3's are going to cancel. I started with 2. I took out 1, I have 1 left. And notice here, if I have 6x and divide by 3x, well, the x's, I took them all, and 6 divided by 3 is positive 2. You don't believe it? Multiply it out. You better get back to what you started with. Now, from here, we could find the zeros. How? Well, take this factored form and set it equal to 0. We have the product of two things equal to 0. So either my first one is 0 or my second one is 0. Well, this is only 0 if x is 0, and here if x is negative 2. Okay. Let's do another example. What if I have 64x squared minus 16x? What do I have in common here? Well, I claim 16x is in common. 64 divided by 16 is 4. I had 2 x's. I pulled out 1. I have 1 left. And notice here I took everything out. So I'm left with a negative 1. Okay. So first thing, if there are common factors, pull them out. Okay. Second stage of factoring. If the quadratic is of the form x squared plus bx plus c. In other words, your a is 1. In order to factor it, what you want to do is find two numbers whose product, in other words, when you multiply them, is c, and whose sum is b. This takes a little bit of practice and it takes some number familiarity. Give yourself some time and space to get this. For example, if I have this guy, what this tells me is I want to find two numbers that multiply up to 6 and add up to 5. What I always do is I write out all my factors of 6 then. So 1, 6, and 2 and 3. So which one of these pairs multiply to a positive 6 and add to a positive 5? 2 and 3. So we can write that as x plus 2, x plus 3. And you can either FOIL this or use the distributive property, multiply this out. I assure you, you're going to get back to where you started. Now look at what happens if I just change one thing. Looks very similar, but now we want to find two numbers that multiply up to a negative 6 and add up to a positive 5. Again, the only numbers that multiply up to 6 are 1 and 6 and 2 and 3. But notice my product is negative. The only way you can multiply two numbers together and get a negative number is if one is positive and one is negative. So having one of these be positive and one of these be negative, which pair will multiply up to a negative 6 and add up to a positive 5? I claim 6 and negative 1. Okay, 6 times negative 1 is negative 6, and 6 plus negative 1 is a positive 5. Okay, what if I have this? Again, it's going to look very similar, but it's going to be different. We want to factor this guy. Notice here now, we want our product to be a positive 6, but our sum to be negative 5. Well, the only way you can multiply to have a positive number is if both are positive or both are negative. In this case, we want to add to a negative number. So the only way this can happen is if both of them are negative. And I claim -2 and -3 work. Notice -2 times -3 is a positive 6, and -2 plus -3 is -5. Okay, what if I have x squared plus 8x? Oh, excuse me. Let's do this one. X squared minus 8x plus 12. Now I want to find two numbers that multiply to 12 and add to -8. I can write all the numbers that multiply up to 12. That's 1 and 12, 2 and 6, and 3 and 4. Notice I want to multiply to a positive and add to a negative. That tells me that both of these must be negative. It's the only way you can multiply up to a positive and add up to a negative. And if both of these are negative, which ones will work to add up to a -8? I claim -2 and -6. All right. What if I have this one? Now you can look at this and say, well, wait a minute. We don't have a 1 in front of our squared term. But remember, the first thing I said to do whenever you are factoring is pull out a common factor. Notice, you can pull out this -2 from each of these terms. If I factor out a -2, I have x squared. Well, I pulled the 2 out. It's going to change the sign. So I'm going to have minus x, and then 4 divided by -2 is -2. Now from here, I'm going to factor this. Notice I want to find two numbers that multiply to -2 and add to -1. Well, if I multiply to a negative number, I know one is positive and one is negative. And if they add to a negative, that means my larger one was negative. All right. So step 3 for factoring. If the quadratic is of the form ax squared plus bx plus c, first thing you want to do is always check for common factors, just like our previous example, to make a equal 1, because then we can use what we just did. But can't always do that. So our steps here then are as follows. You want to find two numbers whose product is A times C and whose sum is B. This is the longest step. The more number familiarity you have, the easier it is to do. Give yourself time. Okay? Our second step then, and you'll see what all this means in a second, because I'm going to go through numerous examples, is rewrite the middle term. By middle term, I mean the bx term, using those numbers found in step 1. And then what you're going to do is do something called factor by grouping. And that is just repeatedly pulling out common factors. Okay, lots and lots of words. Let's do several examples. Okay, so I have about 3 examples we're going to do. You want these steps in front of you. Okay, so how about I say 6x squared minus 13x minus 5. Notice there's no common factor that we can pull out of each of these guys. So my first step is find 2 numbers whose product is A times C. In other words, whose product is negative 30 and whose sum is negative 13. All right, well, what multiplies to 30? We got 1 and 30, 2 and 15, 3 and 10, and 5 and 6. Notice we're going to have one be positive and one be negative because the product is negative. So which combo where one is positive and one is negative is going to add up to a negative 13? I claim 2 and negative 15 are the numbers that work. They're the only ones here that multiply up to a negative 30 and add up to a negative 13. So my next step is to rewrite this middle term using these numbers. In other words, instead of negative 13x, I'm going to have 6x squared plus 2x minus 15x minus 5. Notice this is exactly the same. I just rewrote it using those 2 numbers. Finally, our last step is to factor by grouping. What do I mean by that? Group your first 2 terms and your second 2 terms. Do I have any common factors in my first term? Sure do. There's a 2x in common. If I pull a 2x out of my first term, I have a 3x. And if I pull a 2x out of here, I took it all out, I have a plus 1. Now, what I want to ask is, what can I pull out of my second group so that ideally I'm also left with a 3x plus 1? Well, notice if I want to be left with a positive 3x and a positive 1, and both of these are negative, I'm going to want to pull out a negative number. And 5 goes into 15 and 5. Negative 15x over negative 5 gives me a positive 3x. And I'm left with a plus 1. So I factored each of those by grouping. Notice now I have 2 terms. And they both have a 3x plus 1 in common. So now I can pull that out. And if I pull the 3x plus 1 out of my first term, I'm left with a 2x. If I pull a 3x plus 1 out of my second term, I'm left with a minus 5. All right, let's do another one. What if here I want to do 9x squared plus 6x minus 8? Nothing I can pull out of all 3 terms. So I want to find 2 numbers whose product is the first number times the last number. In other words, negative 72. That add up to a positive 6. Lots of numbers multiply up to 72. We've got 1 and 72, 2 and 36, 3 and 24, 4 and 18. Yikes, huh? 6 and 12, and 8 and 9. Notice one has to be positive and one has to be negative. and they can't differ by very much, right? So which numbers, pair of numbers can we pick where one's positive and one's negative that essentially differ by 6? And I claim it's 6 and 12. And notice since my sum is positive, it's a -6 and a positive 12. This is why I say this is the longest step. Well, what I then do is I rewrite my middle term using those numbers. I have 9x squared, and in place of positive 6x, I'm going to write -6x plus 12x. And then I have -8. This is the only difference. And now I'm going to factor by grouping. What can I pull out of these terms? Well, they have a 3 and an x in common. And if I pull a 3x out of my first term, I'm left with a 3x and then a -2. Again, you're just dividing each of these by 3x. Now I want to pull something out of each of these terms so that I am left with a 3x minus 2. Well, what can I pull out? I can pull out a what? Oops. Sorry, that's supposed to be plus. I can pull out what goes into 12 and 8. We got a 4. If I pull out my 4, what do I have left? Well, 12x over 4 is 3x, and -8 over a positive 4 is -2. Notice now I have 2 terms left. They each have a 3x minus 2 in common. If I pull out the 3x minus 2, in my first term, I'm left with the 3x. And in my second term, I'm left with plus 4. And sure enough, if you multiply these out, you better get back to where you started. All right, one more example. Don't worry, you're going to have plenty of room for practice. Suppose I have 15x squared plus 7x minus 2. Whew. Okay, we want to find two numbers whose product is -30 and whose sum is 7. Well, what multiplies up to 30? 1 and 30, 2 and 15, 3 and 10, and 5 and 6. Notice we want to multiply up to a negative, so one's positive and one is negative. And I claim -3 and a positive 10 work. So I'm going to rewrite my middle term using those numbers. So 15x squared minus 3x plus 10x minus 2. Now I factor by grouping. I can pull a 3x out of my first group, and I'm left with 5x minus 1. And out of my second group, the best I can do is pull out a 2, and I'm left with 5x minus 1. I have 2 terms left. They both have a 5x minus 1 in common, so I can pull those out. Notice then I'm left with 3x plus 2. All right. One more thing with factoring. This is called special forms. The only special forms you really need to have memorized is the difference of 2 squares. In other words, if we have something of the form x squared minus a squared. And I claim you take the first thing that's being squared and add it to the second thing that's being squared times the first thing that's being squared minus the second thing that's being squared. And if you don't believe that this will get you here, you can FOIL it. X times x is x squared. Outside terms is minus ax. Inside terms is plus ax. Last terms are minus a squared. Notice those cancel. All righty. So, what are some examples of that? Well, maybe we have something like x squared minus 9. I claim that's x squared minus 3 squared. The way you'd factor that is you take the first thing that's being squared and add it to the second thing that's being squared, and then the first thing that's being squared and subtract off the second thing that's being squared. Now, these can look a little funkier. What if you have something like 16x squared minus 81? You need to figure out what is the first thing that's being squared and what is the second thing that's being squared. I claim the first thing that's being squared is 4x, right? 4 squared is 16, x squared is x squared. And the second thing that's being squared is 9. So I claim we can factor this by taking the first thing that's being squared and adding it to the second thing that's being squared, and then the first thing that's being squared and subtracting off the second thing that's being squared. All right. I claim this is difference of 2 squares, almost. Remember, the first thing that you're supposed to do whenever you factor is pull out what's in common. We can get that 5 out of there, and we're left with x squared minus 1. Now, you might ask, how in the heck is this the difference of 2 squares? I claim that's x squared minus 1 squared. So we can factor that as x plus 1, x minus 1. All right. So let's just factor this. Let's factor this completely by grouping. Putting some of our ideas together. Notice there's nothing we can pull out of all 4 of these terms, which is a total bummer, but we can group them. What do these 2 terms have in common? They have a 4x squared. I pull a 4x squared out of my first term, I'm left with an x. And here I'm left with minus 3. Now, I want to be left with a positive x and a negative 3. So what I'm going to do is pull out that minus 9 so that my first term then is a positive x. And notice 27 over negative 9 is negative 3. I have 2 terms. They have an x minus 3 in common. Notice if I pull out the x minus 3 from my first term, I'm left with a 4x squared. And out of my second term, I'm left with minus 9. But I claim this is not fully factored. Okay? This second term, I claim, is the difference between 2 squares. Right? 2x quantity squared is 4x squared, and 3 squared is 9. So to fully factor this, we have an x minus 3, and then we can factor this by saying it's 2x plus 3, 2x minus 3. Now, this is the special form that comes up a ton. Okay? There are other special forms that arise. But there's no need to memorize. okay? And this is the sum and difference of two cubes. In other words, if you're adding two things that are being cubed or subtracting two things that are being cubed. And what I'll say, if you want to see what this looks like, is when you have x cubed plus a cubed, you take the first thing that's being cubed, add it to the second thing that's being cubed, and then you take the first thing that's being cubed and you square it, minus the product of those two, plus the second thing that's being squared. And this one's going to be just the opposite in terms of those signs. You can use the distributive property to prove to yourself that you have equality here. So just as an example, x cubed minus 8. Well, I claim that's x cubed minus 2 cubed. So using this structure right here, we would factor that to be x minus 2. We'd have x squared plus 2x, and then finally plus 2 squared, or 4. Okay. So next, what I want to say is as follows. Factoring is sweet. Okay. What if I wanted us to factor this? Well, notice we'd want to find two numbers. There's a 1 in front of the squared term whose product is -4 and whose sum is -4. Well, the only things that multiply to 4 are 1 and 4 and 2 and 2. And if the product is negative, one is positive and one is negative. Okay. Well, I claim there's no way to do this. Okay. Right? 1 and 4, there's no way for one to be positive and one to be negative to add up to 4. And 2 and 2, there's no way for one to be positive and one to be negative and add up to a -4. This is not factorable. Bummer. Okay. Factoring is so fun, but it doesn't always work. That is why we need our other methods of completing the square and the quadratic formula. And that we will leave into our next video.